Every day, millions of kilograms of cassava roots arrive at this facility. These roots are the starting point of an industrial process designed to extract one of the world's most versatile natural materials, starch. Cassava grows underground, which means every root carries soil, sand, and organic debris. If these impurities are not removed immediately, they can damage machinery, contaminate the starch, and reduce final product quality. Before any machine touches the roots, trained workers perform a visual inspection. Diseased or damaged cassava is removed early, preventing unwanted bacteria and off quality material from entering the system. Once approved, the roots move onto automated conveyors. This controlled flow ensures uniform processing and prevents mechanical overload in the washing stage. Inside the rotating washing drums, high pressure water jets do the heavy work. The tumbling motion forces cassava roots to rub against one another while water penetrates every crevice, lifting away soil without damaging the starch rich interior. This step is critical. Clean roots protect downstream equipment and guarantee that the starch extracted later remains pure, bright, and consistent. As the cassava exits the washer, excess water drains away. What remains is a root that is clean, intact, and ready for precise mechanical processing. This is where transformation begins. From raw agricultural harvest to controlled industrial input, washed, inspected, and prepared for conversion into silky starch. After washing, the cassava roots still carry an outer skin. This peel protects the plant in the soil, but in starch production, it becomes an impurity. Mechanical peeling drums remove this outer layer with controlled abrasion. The goal is precision, not force. Too aggressive and valuable starch is lost. Too gentle and unwanted fibers remain. Water is continuously added during peeling. This reduces friction, prevents heat buildup, and immediately carries away loosened skins, keeping the roots cool and intact. Once peeled, the cassava moves quickly to the grating stage. Timing matters here. Fresh cassava begins to oxidize once exposed, and rapid processing preserves starch quality and color. Inside the grating machines, steel surfaces shred the roots into a fine, wet pulp. This step breaks open the plant's cell walls, releasing microscopic starch granules trapped inside the fibrous structure. Water is added again, not to wash, but to suspend. By turning solid cassava into a flowing slurry, the starch can now be separated using gravity and centrifugal force. This transformation is essential. Starch cannot be extracted from solid roots. It must first be freed, suspended, and prepared for purification. What leaves the grater is no longer a root. It is a starchy slurry engineered for separation, refinement, and control. At this stage, the cassava is no longer solid. It exists as a flowing mixture of water, starch granules, and plant fibers. The challenge now is separation. Starch is heavier than water but lighter than fibrous material. This difference in density allows engineers to separate components without chemicals using physics alone. The slurry is first sent into hydrocyclone separators. Inside these cones, the mixture spins at high speed. Centrifugal force pushes heavier fibers outward while fine starch remains suspended toward the center. This controlled spinning creates order from chaos. Unwanted material is continuously removed while clean starch flows forward. Next, the purified slurry enters settling tanks. Here, time replaces motion. As the flow slows, gravity takes over. Microscopic starch granules gradually sink, forming a dense layer at the bottom. Clear water rises above and is recycled back into the system, reducing waste and conserving resources. This step defines starch purity. If separation is incomplete, fibers will affect texture, color, and performance in final applications. What emerges is a smooth, uniform starch paste, free from grit, free from fibers, engineered for consistency. This is the moment where agricultural material becomes an industrial ingredient, measured, predictable, and ready for refinement. The starch leaving the settling tanks is pure but still heavy with water. To become usable, this moisture must be removed with precision. The process begins with mechanical dewatering. Centrifuges spin the starch paste at high speed, forcing free water outward while dense starch remains behind. This step is about efficiency. Removing water mechanically uses far less energy than heat alone and protects the starch from damage. Even so,